Okay, so let us continue. So yeah, we were talking about these multivariate regression line. It is W1x1 plus W2x2 plus and so on. You can write it in the same form as we were writing it in the simple two-dimensional line. But here you can always say that we are not getting what it means by the intercept. So intercept could be the variable, let us say W1. You can say that W1 is the one which is, or maybe I can introduce a W0. So along with this W0, you will have the complete equation of it. But without intercept, the equation works like this: W1x1 plus W2x2, etc. So don't get lost in these terminologies. You will understand more when you will also have an opportunity to do it on your own. I will get you the Python program maybe in a week or so as a practice exercise to compute every error which we are having in this discussion and use certain things, certain algorithms to reduce those errors. Okay. So when we talk about the error surface for linear regression in one variable, you can understand that x1 is that observation's first value, y1 is the first value of the first observation. Similarly, x2, y2, xm, ym, etc. are the pairs of x and y values. Any hypothesis hw, why I am writing hw for f is only because its optimal characteristic is represented by hw that approximates the function that fits best to the given values of y. So there is likely to be some error corresponding to each observation, say I. The magnitude of such error is yi minus hwxi. Why should I write it like this? Here you need to understand what it means by this. Yi is the actual value. Actual value, how did we take in the previous computation? It was taken as y, and hwxi was taken as p. So basically what we took as p earlier is obtained by this computation hwxi, right? Hw is the name of the function. Its expression is given by w1x1 plus w2x2, etc. And xi is the ith observation whose interaction with the line gave us this y point, which is nothing but p. So you are going to optimize this error for the minimization of yi minus hwxi square. So what we did earlier was the summation of y minus p whole square, right? And then we took the sum of it, right? You took sum of it for all the observations, and then you understood which is the minimum. Okay, so with this we are going ahead to see the linear regression in two variables. Let us say there is one variable x1 which is the number of hours for work, number of hours of work which people did for a company, and number of items produced is in these values. Every data is numerical, and average wages paid to each employee. So each employee was paid some 300 rupees or 220 rupees. It is distributed on the basis of the production, right? So the number of hours put in by them and the number of items that they produced, right? If they had put in less number of hours in that week or month and they produced less number of items, then the wages were less. It is accordingly. So here there are two variables, and the wages each employee will get will be dependent on these two variables. So it is just a fictitious example. Now you can understand that instead of a line, there is a plane that is to fit this entire data. How will you visualize this data? It is on x-axis or x1 axis it is 89, on x2 axis it is 4, on the z-axis, right? I am calling it as a y variable, but let us say it is the third axis. On the third axis it is 300. When you will plot these three-dimensional points, they will be suspended in the three-dimensional Cartesian plane, Cartesian system, and then you will have to check whether there is a plane passing through most of the points, or which plane will pass in such a way that the squared errors are minimum. Okay, so this is one visualization of the two variables based regression. So don't get confused with the calculations. I will give you the code where you will see exactly how things are happening and how you are computing the errors. Okay. So then there is a linear function in two variables, right? Each pair W1, W2 corresponds to a line given by these equations, equation 1, while only one such pair corresponds to the line that best approximates the given data. Okay. So you have already seen this visualization where W1, W2 corresponds to the minimum error. There are several techniques in machine learning which help us in reaching this global minimum. Why I am calling it as global minimum is because there could be a point corresponding to which there exists this pair W1, W2, but it appears to be the minimum error, but there is still a much less error existing corresponding to another pair of W1, W2. So rather than getting stuck in the local minima, we always want to reach the global minima and find the corresponding W1 and W2. So there are techniques which give us the ways to avoid local minima. There are ways to reach the global minima, and several evolutionary algorithms like partition form optimization, etc., would help in reaching the global optima faster. The basic technique in reaching the global minima is gradient descent, where it doesn't guarantee that it will not stuck in the local minima. So all these things are just going to create your curiosity that machine learning is not that straightforward as it appears to be. Here, the system has to learn through dignified algorithms where it has to have a way to find the learning parameters, right? So computer cannot run on its own. It has to have definite mechanisms. So from the data, you have understood that the system has ways to calculate the error. The system will have a definite algorithm to calculate the minimum error and find the corresponding parameters of the line or the regression curve, and then it will be able to predict. So as I told you in the beginning that there is nothing artificial intelligence, there is nothing like artificial, there is everything which is computational. So here also the learning is imbibed in the systems through calculative components, through these computations. We will have definite algorithms to make the systems learn. Right, so here we are seeing that the systems are made to learn prediction of the value, the prediction of the value of the dependent variable, where different other past experiences form the data for it to compute the error, and then it has a separate set of algorithms which we have not yet discussed regarding how to get to the global minima of the error from whatever values of W you assumed, right? So this is still a visualization of f of x1, x2, x3. If my environment for the learning system was described by three variables, say for example humidity, temperature, and some other parameter like pressure of the air, then we need to predict the rainfall. Then we should have the observations about the past 5 years of the data regarding whenever, whatever the value of the air pressure, the humidity, the temperature, in that combination, whether it rained or not or how much it rained. These four observation values should be there with us so that we can predict it for the time when we have a set of x1, x2, x3 values as the testing data. And in that case, we are not expecting y to be known. We are expecting our system to tell the value of the y. Fine. So we have this kind of hypothesis for three-dimensional space. I've just tried to show you this in the four-dimensional space where the fourth dimension represents the error. The first, second, and third dimensions represent the values of W1, W2, W3, right? The hypothesis construction will be W1, Wx1 plus W2, X2 plus W3, X3. And it is actually a line in three variables. You can always visualize a line going from one corner of the room where you are sitting to the other extreme opposite diagonal corner of the room, which is cubic in its nature. Or even if it is rectangular, you will always find a line visualization in the three-dimensional space. And this is still being a line exists in the three-dimensional space. That is one equation which is relevant to one combination of W1, W2, W3. If you will visualize how this line will plot on W1, W2, W3 space, this line can be plotted as a simple point representing W1, W2, W3. Right? So, yeah, the shadow I have just shown is to get you the feeling that this is a four-dimensional space. Of course, we cannot visualize it. We just assume that it exists. And mathematically, you can even work with 100-dimensional spaces. You can know how to compute the Euclidean distance between 2 points in 5-dimensional space. It will be the sum, the square root of the sum of the square differences between the corresponding ordinate values, right? So then here it is another example of polynomial curve learning where there were these points. You could fit in a polynomial, or you could fit in a straight line, or a higher order polynomial. Okay. So here you can see that if we have x as a univariate data with 1, 0, 0, 1. So the value of y, the actual output is 0, 1, minus 1, 0.8, minus 0.8. Just looking at the data, we humans also could have got confused. What is this curve? Whether it is a line or a parabola or a circle or ellipse, we do not know unless we plot all these points. But the moment you plot all these xy points, you know that it is a circle. So now if you have to predict the value of f of minus 0.25, you can always very well get it through the equation. So what is the equation of a circle? Can you tell? Anyone can tell? What is the equation of a circle? Yeah, it is x square plus y square equals r square. Yeah. If you're taking it as x square plus y square equal to 1, then it will be having a radius of size 1. If it is r square, then it has the radius of r square. Yes, good. So when you are taking it as x minus h square plus y minus k square equals r square, this means that the center of the circle is at hk and its radius is r. So you all know the equations of circle. So What will be its parametric form? Can you tell? The parametric form of a circle. Can you expand this? Yeah, there are these students, Venkat, Pranav and Arun, who have given these definitions of circle. So if I'm writing x square, okay, I will write it as x square plus y square. So let me write it as, or maybe, okay, just give me some time. I will write this equation. Yeah, so yeah, Shrikant is giving a different definition of the circle. It is x equals r cos theta and y equals r sin theta in the different coordinate system. Okay, so if you're writing it like this, say x minus h square, okay, and plus y minus k square equals r square. So if you will expand these squares, what will you get? You will get x square minus 2hx minus plus h square plus y square minus 2yk plus k square equals r square. So how can you write it in the most generic way? It will be x square. Okay, so I am writing it like differently so that I don't have to switch between the squares. X square plus y square. Okay, sorry. Okay, y square plus what is it going to be? Minus 2hx minus 2yx 2ky plus h square plus k square minus r square, yeah, equals 0. So what is its parametric form? It will be x square plus y square. You can write it as ax square plus by square plus cx plus cy plus d equals 0. Or if you want to divide everything by the similar variables, because it is a circle, you can always write it as x square plus y square plus ax plus by plus cx, c, right? So that means there are three variables that define a circle. You could call them as W1, W2, W3. That means a circle in two-dimensional space can be described by three variables and not two as we were having in the case of line, right? So, yeah, are you able to see this? X square plus y square minus 2hx minus 2ky, okay? So, if you write this equation in the form of the parameters, then you will see that minus 2hx can be written as ax, or if you want, you can see that h, k and r, these themselves are the three parameters. If you know their value, then you know the equation of the circle. So circles can be different in their sizes. Circles can be different in their positions. But of course, they are not going to give us a linear curve which fits some linear data. Here, the data is more complex. It is distributed in such a way that we cannot at all fit a line. So we have to go for a second order curve, which is by chance a circle. It could have been a different curve. It could not have been a circle at all. So we always visualize these lines or these curves as the parametric curves, where certain number of parameters define these curves. Okay? Yeah. So we do not need to know if a function is linear or circle or polynomial. We keep trying the errors, and if you see that it is not linear, then you will have to change your model. That will come quite later when we will discuss the hypothesis form as a non-linear form, right? So here I am just trying to tell you the difference between uh, the functions which need to be approximated for the linear data and for non-linear data. Okay. Later on, we will be using some kernel methods to translate or transform these non-linear parametric forms into the linear ones. Okay. So this is also kind of overview that I'm giving, but in today's lecture, you need to learn one major thing, which is the squared mean error for the given data, which is approximated by a line, either in two-dimensional space or in one-dimensional space or in three-dimensional space. You need not worry about the non-linear approximation. It is just a kind of overview of the non-linear approximation. Fine. But the major focus of today's lecture was in approximating a line for the given data. The data is discrete in nature, but then line formulation will be ready to predict any other unseen or seen data, as if you had a continuous polynomial or continuous line available with you. Okay, is this fine? So for today's lecture, I had only this much schedule for discussion. If you have any more doubts, you can ask, and then by the next week you will get certain practice sheets for coding in Python. Yeah, the difference between global and local minima. Global minima is considered to be the one value which is even lesser than the local minima. It is something as if you are being given some certain awards or some marks, and when you are given marks, you feel that okay, yeah, out of 50 I'm getting 35. That is pretty good. It is almost the maximum. This is maximum rather, because you know some of your friends' marks, they were 31, 30, 29 and 15. But this was the local maxima, while there existed another person who got 40 out of 50 marks. I would say that 40 marks were the global maxima. Similar occurs for the local and global minima in the reverse direction. Is it okay? The difference between global and local minima. So how is error approximation leading to learning? Yeah. So once you have obtained the weights, right, which are the best weights, we will continue these discussions for learning part in the next class. So I will give you a hint that once we have this equation of y equals wx in the most simpler sense, when it is a line in univariate data, it is the line fit for the univariate data, and once you know the slope, then if there comes a value of x for which you have to predict the value of y, knowing the value of x and knowing the value of w, you can always compute y, which is the predicted value. Okay. So a book link I will try to give you early. So today's class will be all the classes will be uploaded as recording either today or tomorrow. Okay. So the question regarding how to or why to take global or local minima. Shivam, I'm not very clear what you want to ask here. Why do we need to calculate or take global or local minima? So if we are actually happy with local minima, it will be something as if we are approximating very harshly, very less efficiently, and whatever will be the predictions, that will not go so good. Your accuracy will still be lesser. Okay. Course handout is uploaded right now. There will not be major changes, but some more changes I will be mentioning in the revised handout within a week. Okay. So there is no courseware, as I told you in the last class. We will have our live lectures and we will go with that. Okay. So yeah. So handout with all the textbooks that is already uploaded. Yeah. So textbook is already there. You start reading this. The link is also given most probably. Otherwise, I'll give you another link. So keep reading. I will give you the updates as and when they are available. Yeah. Okay. So what is the use of global minima and local minima that I explained? That with global minima, you are bound to get the best accuracies of prediction. With local minima, you may likely get less accurate results of prediction. Okay. So last circle problem I will pick up in the next class most probably. Yeah. So course handout will be slightly revised, not in the major chunk, but mostly the things will remain almost same, but I will check the contents here. Yeah. Christopher Bishop, Pattern Recognition and Machine Learning, it is a costlier book, so you can check out if it is available on the net. Yeah. Yeah. Tom Mitchell is also a good book. It is so far a textbook. So textbook you can refer. Yes, definitely. As I told you that Python learning, I will give you some more links and some more practice exercises. Yeah. So Tom Mitchell is a good book for you to read. If you purchase, it is good. So I think 26th January we will not have the class, right? So the class schedule is uploaded one day before. You can keep checking. Yes, Python is needed. I'm sorry. Yeah. So that we need to learn. What is that? Generic Python programming. Yes, you have to. Okay. Yeah. Yeah, sure. So as the classes move on, you will keep getting something or the others for practicing, and you will learn slowly. But you need to also put yourself motivated and keep attending the classes, and definitely you will grow. Yeah. So we will actually focus on Python-based coding for this understanding, and otherwise you can use any other thing, but your assignment will be based on Python. Yeah. Sure. So you will get some examples and solutions as well. Yeah. Priyaranjan, we will give you. Yeah. Not now, but later. Fine. So I'm closing this session now, and then we will meet next week, probably on Sunday. I think the class is not there, but you keep having an eye on the schedule. The class will be on 27th and not on 26th. Fine. So I'm closing it here. Okay. Have a nice day.